Hey HMS modelers, this is Mike Bartles from the Hydrologic Engineering Center. In this lecture, I'm going to introduce reach routing within HEC-HMS. And this lecture is part one in a series of lectures just devoted to simulating open channel flow processes within HEC-HMS. I got to note that a good bit of material that was in this lecture was originally developed by Gary Bruner, who's also from HEC. This lecture is meant to serve as an introduction to channel routing and will not be an exhaustive, detailed look at everything that is contained within HEC-HMS. Just a heads up, we will spend a bit of time looking at equations in the beginning, but it's important to look at the equations to understand how hydrologic routing differs from hydraulic routing. Afterwards, we'll talk about the various ways in which reach routing can be simulated within HEC-HMS. As runoff from subbasin elements reach defined channels, as shown in the left-hand image, depths increase and the predominant flow range begins to transition to open channel flow as shown in the right-hand image. Now at this point, open channel flow approximations are used to represent translation and attenuation effects as flood waves move downstream. Open channel flow modeling, or reach routing as it's referred to within HEC-HMS, is an approach that is used to predict the temporal and spatial variations of a hydrograph as it moves through a river or a stream. The effects of storage and flow resistance are reflected in changes in the hydrograph shape and timing as the flood wave moves from upstream to downstream. The figure shown here demonstrates the major changes that can occur as a hydrograph moves through a reach. Specifically, the blue inflow hydrograph is translated or shifted in time, and the peak inflow is reduced or attenuated to produce the pink outflow hydrograph. Here's an example application within HMS that uses reach routing. Within this simple model, the runoff from two subbasin elements are combined and routed through a single routing reach element. In the routing reach, the blue inflow hydrograph is attenuated and translated to produce the black outflow hydrograph. Reach routing is used in nearly all hydrologic modeling applications, from flood forecasting to sediment transport. Now, each of these example applications may require different levels of detail and outputs, and as such may require different reach routing approaches. In general, routing techniques may be classified into two categories: hydraulic routing and hydrologic routing. Hydraulic routing techniques are based on the solution of partial differential equations which govern unsteady open channel flow. These equations are often referred to as the St. Venant or dynamic wave equations. Hydrologic routing routines employ the continuity equation and either simplified forms of the momentum equation or very simplified relationships between storage within the reach and discharge at the outlet as a replacement for the momentum equation. The equations that describe one-dimensional unsteady flow in an open channel consist of a continuity equation and a momentum equation as shown here. The solution of these equations defines the propagation of a flood wave with respect to distance along the channel and time. Solved together with the proper boundary conditions, these equations are the St. Venant or dynamic wave equations. Depending on the relative importance of the various terms of the momentum equation, it can be simplified for various applications and not lose too much predictive power. Approximations to the full dynamic wave equations are created by combining the continuity equation with these various simplifications. And the most common approximations of the momentum equation are shown here and include the kinematic wave, diffusive wave, and quasi-steady state dynamic wave approximation. The use of approximations to the momentum equation can be justified when specific terms are small in comparison to the bed slope. And this is excellently illustrated by an example taken from Henderson's 1966 book titled Open Channel Flow. In this example, Henderson computed values for each of the terms on the right-hand side of the momentum equation for a steep alluvial stream when subjected to a very fast rising flood hydrograph, in which the flow went from 10,000 CFS to 150,000 CFS and back down to 10,000 CFS within 24 hours. Even in this case, where changes in depth and velocity with respect to distance and time are relatively large, the last three terms are still small in comparison to the bed slope. For this type of flow situation, an approximation of the full equations can be easily justified, but that's not always the case. The use of either the hydraulic or hydrologic routing routines that have been described so far assume that 1. Velocity is constant and the water surface is horizontal across any channel section. 2. All flow is gradually varied, with hydrostatic pressure prevailing at all points in the channel, thus vertical accelerations can be neglected. 3. No lateral or secondary circulation occurs. 4. Channel boundaries are fixed. Erosion and/or deposition do not alter the shape of a channel cross-section during the simulation. And 5. Water is of uniform density and resistance to flow can be described by empirical formulas like Manning's or Chazy's equation. There are 8 hydrologic routing methods available for use within HEC-HMS. Additionally, version 4.7 introduced the 2D diffusion wave transform method, which can be used within a subbasin element to route a flood wave using the diffusion wave hydraulic routing approach. Each one of these approaches uses different approximations of the continuity and momentum equations, and we'll go through a few of these hydrologic routing methods in future lectures. You can estimate many of the required parameters for each of the aforementioned routing methods using readily available GIS data sources. For instance, stream alignments can be found within the National Hydrography dataset, elevations can be sourced from the National Elevation dataset, and land uses can be extracted from the National Land Cover database. Several reach characteristics, like length, slope, relief, and sinuosity, can also be computed directly within HEC-HMS. Now I'll go into greater detail regarding parameter estimation for specific routing methods within future videos. In review, within this video, I introduced reach routing within HEC-HMS. I also compared hydrologic routing and hydraulic routing and delved into some of the assumptions that are made when simulating reach routing. I also quickly discussed parameter estimation, but I'll revisit this topic in future videos. Within the next few lectures in the series, we're going to look at a couple of routing methods that are available for use within HMS in greater detail. First up is the lag method. I'll see you then. Thanks for watching.